Good afternoon, Highlanders. Another great day to be a Highlander. Every day is a great day to be a Highlander if I'm out of focus. I think I'd be good at this by now. That's not good. Try it again. That's better. All right. Okay. So 11.3 is another special formula, I guess, kind of like another result that you get when you cross two vectors. Just like the dot product is a special calculation, that's kind of what this is too. And they use this x to determine or mean cross product, right? So when you see u, x, v, that means we're crossing those two vectors. So that's u cross v. And what you get is a third vector. And so the formula reads as such. And if we were in class, I would have went through and showed you how to use determinants in matrices and how that ties into here. Because, and you can look at it in the book, but if you remember how to find determinants, it's always the matrix of the minors that you get when you cross out rows and columns, and they go through it. But we're just going to go ahead and use the formula, so you'll have it there to use. And so we take u2, v3, that product, minus u3, v2, and this becomes the x-coordinate of the third vector. And then it's u3v1 minus u1v3, and that's the y-coordinate of the new vector. And then it's u1v2 minus u2v1. So that is the formula for the cross product. So let me go through and grab a couple vectors and show you how this works. Let's say u is 1, 3, negative 1, and v is 2, 1, negative 2. Okay, now u cross v, so remember we're taking the second u times the third v, so that's negative 6. 3 times negative 2 is negative 6, minus u3, which is negative 1, times v2, which is negative 1. Right, so negative 1 times negative 1 is negative 1, so that becomes a plus 1. Then it's u3 times v1, so that's negative 2, minus u1 v3, so that's also negative 2, so that becomes a plus 2. And then the third coordinate, we have u1 times v2, so that's 1, minus u2 times v1, so minus 6. Or negative 5, 0, negative 5. So this is the vector u cross v. Whoop-de-doo, you're saying, right? But what its significance is that this vector right here, the cross product vector, is orthogonal to both u and v. Or in other words, if this is u and this is v, this vector is u cross v. It's perpendicular to both u and v. Right? So it becomes an axis that they can spin about. It becomes extremely important when we start talking about equations for planes, which we're going to do in the last section. So that's the most important thing that the cross product does for you, is that it gives you a vector that is orthogonal to both u and v. And if you wanted to, we could check to see if this is true by calculating the dot product. So if I were to take this and dot it with the cross product, what we should expect to get is 0, right? So we got negative 5 plus 0 plus 5, which is 0. So we take the cross product dotted with u, we get 0, which means they're orthogonal. We do the same thing here. So we get negative 10 plus 0 plus 10, also 0. So again, the significance of the cross product is another vector. Remember, dot products give you numbers, cross product gives you a vector. And that vector, or any scalar of that vector, will create another vector, a third vector that's perpendicular to both the other two. Okay, there are some geometric properties here, which you'll see when you do your book notes. The first one, obviously, is that the cross product is orthogonal to both. So u cross v is perpendicular to both u and v. The second thing that's true is that when you take the magnitude of the cross product, remember magnitude is the distance, cross product is a vector, so when you take the magnitude, and it becomes equal to the magnitude of u times the magnitude of v times the sine of theta. Now, what's critical about this? U and v sine theta. This is like AB sine theta. If you are remembering, when that was theta and we took the side angle sides approach to this, this is how we found the area of that triangle. Do you remember that? So obviously this now becomes some sort of area process here, which we'll get to in a minute. U cross V equals 0 if and only if u and v are parallel, which means if they're parallel, they're scalars of each other, and this area, 1/2 AB sine theta. Remember that formula? Right? So AB sine theta becomes twice the area of this thing, which is going to be what? A parallelogram. So this cross product, when we take its magnitude, is the area of a parallelogram with u and v as sides. So that's kind of neat. We can have two vectors or get two sides, and all we got to do is calculate the magnitude of the cross product, and you are getting the area of the parallelogram, which means that what is this? This is also the area of that parallelogram. Right? So this was the area of the triangle. All we did was double it. Okay. So that's kind of the importance of that. There's a couple other real neat things that we're going to talk about here, some more geometry behind the cross product. Something called the triple scalar product. And the triple scalar product is just this. When you take and you have three vectors, so you have vector u, vector v, and now vector w. When we take u dot v cross w, we get what is called the triple scalar product. Now, again, all we're doing is crossing these two and then calculate the dot product. So this, again, this is a vector, and then when we dot it with another vector, we're getting a number, and that number is considered the triple scalar. The significance of the triple scalar, so if we think about what this kind of looks like, if u and v and w looks something like this, right? They can form the three sides of a three-dimensional shape, which looks like this. Right? And so these are, again, these are parallelograms. I didn't draw that in there very well, but this would be over here. Sorry. And then we got this and this. So ignore that. So what we end up with is something that looks like a prism. However, because these are not the same length, this is a sort of each face being a parallelogram, so it's like a three-dimensional parallelogram prism, right? Even though it's not a prism because it's not right. Oh my gosh. Parallelogram. There we go. Prism. So that's what you can think of it like. It has a special name. It's called a parallelopiped. Right? So it's like a box that's been smushed over. Right? So let me see if I can. So you got your box, right, and you just smush it so that all the faces are parallelograms. Which is what we got going on here. I didn't draw that very well, but you get the idea. So take your cube, take your box, and then just smush it over. Right, the top goes that way and the bottom goes that way. So it ends up being something like this, where you have a parallelepiped. Awesome drawings. Okay, anyway. Now, the significance of this number, though, right? So remember what u cross v has to do, right? U cross v has to be this vector that is perpendicular to both u and v. Oh, I'm sorry, v cross w. Right? So it's perpendicular to that one, and it's perpendicular to that one. So this becomes that vector, right? Perpendicular to both. When we perform this action, we get a number, right? And that number, believe it or not, is the volume of the parallelepiped. So when you tap three vectors and you calculate the dot product of the third vector with the cross product of the other two, you get the actual volume of that parallelepiped. So that's the significance of the triple scalar. Let me show you an example of that, how that all works. Let's say we have here's an example of where we want to find the area of a triangle with these 3 points as vertices. 1, negative 4, 3, 2, 0, 2, and negative 2, 2, 0. So this is some triangle in space, and we want to find the area of that triangle. So what we're going to do, and let me just name these as A, B, C. Those are my 3 points. That's triangle A, B, C. Some triangle in space, and we want to find its area. So what we need to do is we need to turn this into 2 vectors. So I'm going to use A as sort of my initial point of those 2 vectors. So I need to find vector AB, and I need to find vector AC. So vector AB is going to have the components. So this I'm using as my same initial. And again, you could use B, you could use C. It doesn't matter. But whatever one you pick to be your initial point, it has to be the initial point for both, because you're going to use that to slide the vectors back to the origin so that I can do a calculation. All right, so again, sliding 2 minus 1 is 1, 0 minus a minus 4 is 4, and 2 minus 3 is negative 1. And then vector AC is negative 2 minus 1, 2 minus a minus 4, and 0 minus 3. So now, by translating, we still have the same size triangle, right? If we were to draw this out, we would still have the exact same congruent triangle because all we did was translate. But now, if you remember a few minutes ago, if I were to look at the magnitude of AB times the magnitude of AC sine theta, this becomes the area of the parallelogram formed with those 2 sides. So if we cut it in half, now we have the triangle area. So we have almost everything we need here, with the exception of, so we have 1/2. We'll get to this in a minute. So the magnitude, 1, remember we're the square root of a squared plus b squared plus c squared. So that's 1 plus 16 is 17, plus 1 is root 18. The magnitude of AC, or the length of AC, 9 plus 36 is 45, plus 9 is 54, sine theta. Now, how do we find theta? Well, theta is the angle between, right? It's the included angle between those 2 vectors. So the cosine of theta is equal to the dot product of the 2 vectors. So the dot product is negative 3 plus 24 plus 3 over the product of the magnitudes, which we just did. So again, to the calculator we go. We have, turn the contrast down a bit, there we go. So we have cosine inverse of 24 divided by this product of root 18 times root 54, and the angle between the vectors is about 39.66. So theta is about 39.66. So now we can plug that in here. And now we can find the area of the triangle in space is, my batteries going dead. 0.5 must be the end of the year, times root 18 times root 54 times the sine of theta. So the area is about 9.95 square units, and that would be the area of the triangle. Double that, and formed by these, these 3 points formed by these 2 vector sides. Double that, and you get the area of the parallelogram with these 2 sides. So again, we can use everything that we've kind of learned to find the area of a triangle. If we want to find a vector that's perpendicular to 2 others, that's straight up calculate the cross product. And to find the volume of a parallelepiped, let's say, I'm going to do question 56 here. Let's say U is written as I plus J plus 3K. V is 3J plus 3K. And W is 3I plus 3K. Okay, so again, three vectors, right? They form the sides of the edges of a parallelepiped, and we want to find the volume of the parallelepiped. So this is written in that linear format, so we're going to go ahead and get my three vectors. So the coefficients are those, 1, 1, 3 is U. I is 0 here, J, K, and here, J is 0. So those are your three vectors. So again, we want to perform the triple scalar product, which is U dot V cross W. So U, 1, 1, 3, and then we got to perform the cross product, and again, going back to that formula between these two, so it's U2, or in this case V2, times the third one, so that's 9, minus 3 times 0. The second one is the third times the first, which is 9, minus the first times the third, which is 0. And then the last coordinate in the cross product is the first times the second, which is 0, minus the second times the third, second times the first, sorry, which is 9. So we have 1, 1, 3, dot, 9, 9, negative 9. So the dot product of the x's, plus the product of the y's, plus the product of the z's, which is minus 27. And so 18 minus 27 is negative 9. And you might say, wait a minute though, how come it's negative? Well, it's just because it's more directional than anything. So whenever you're doing the volume here, it's always absolute value. And that becomes the volume of the parallelepiped with those three vectors. So what happens if they give you vectors that are just points? Like maybe they give you all of the vertices of the parallelepiped, which they do in questions 59 and 60. My suggestion, graph it, right? Graph it and then grab the three edges and use those as your vectors. And you'll have no trouble. So again, we're getting used to the cross product. What it tells us another vector, and that vector is perpendicular to the other two. So that would mean that this vector is perpendicular to both V and W, right? Because that's the cross of V and W. And then we have the triple scalar, which gives me the volume. We have our special area formulas that we developed early on with our trigonometry. And a lot of cool stuff that you're able to do here. But again, just a lot of using formulas and calculating. So yeah, that's about it for 11.3. So far, we're just sort of building. We're using dot products, we're using cross products and what they mean, and then ultimately we are going to convert all of this into lines, equations of lines in space, and equations of planes in space. So we have one more section lesson to go. So I'm going to close this also with a joke. What has 4 wheels and flies? 4 wheels and flies. A garbage truck. There you go. It's your joke of the day. All right. Have a great day, Highlanders. Mr. Lampkin is out.